Can sound create light? The enigma of sonoluminescence. Imagine a world where sound could create light. A world where a symphony could ignite a city, where a whisper could illuminate a room. Sonoluminescence is the emission of short bursts of light from imploding bubbles in a liquid when excited by sound. The story of sonoluminescence begins in a lab in 1934. Researchers at the University of Cologne were experimenting with sonar when they noticed something peculiar. Their equipment, designed to use sound waves to detect objects underwater, was producing tiny flashes of light within the liquid. This wasn't just some faint glow, these were distinct bursts of light, each one synchronized with the sound waves passing through the liquid. It was like the sound was somehow compressing energy within the bubbles, forcing them to release it as light. How could sound, a form of mechanical energy, be transformed into light, a form of electromagnetic energy? The early years of sonoluminescence research were marked by a lack of understanding and a sense of awe. But as scientists delved deeper, they started to unravel the complex interplay of physics at play. To understand sonoluminescence, we need to first understand the nature of sound and its effects on liquids. Sound travels through materials as waves of pressure, compressing and decompressing the medium as they propagate. Think of a stone dropped in a pond. The ripples spreading outwards are analogous to sound waves traveling through air or water. When these sound waves encounter a bubble in a liquid, something fascinating happens. The bubble acts like a tiny resonator, expanding and contracting in sync with the pressure variations of the sound wave. Now imagine increasing the intensity of the sound. The bubble's oscillations become more violent, growing larger with each cycle until it reaches a critical point. This extreme compression within the collapsing bubble is key to sonoluminescence. The energy concentrated in this tiny space excites the atoms inside the bubble, releasing photons, the fundamental particles of light.
While sonoluminescence occurs sporadically in nature, scientists have devised ways to recreate and study this fascinating phenomenon in the lab. The basic setup for a sonoluminescence experiment is surprisingly simple. It involves a flask filled with a liquid, typically water, and a pair of piezoelectric transducers placed on opposite sides. These transducers, when subjected to an alternating electric current, vibrate at a specific frequency, generating the sound waves that drive the sonoluminescence. The frequency of these sound waves is crucial. It needs to match the natural, resonant frequency of the bubbles within the liquid. Achieving stable sonoluminescence requires precise control over several factors, including the frequency and intensity of the sound waves, the liquid's purity and temperature, and even the size and shape of the flask itself. Despite these challenges, scientists have made significant progress in understanding and controlling sonoluminescence in the lab.
Section 4. Nature's Symphony of Light, the pistol shrimp's sonic weapon. While we often think of sonoluminescence as a laboratory curiosity, nature provides a stunning example of this phenomenon in action. The pistol shrimp. This tiny crustacean, armed with an oversized claw, has mastered the art of weaponizing sound. With a quick snap of its claw, the pistol shrimp generates a cavitation bubble that, upon collapse, produces a shockwave powerful enough to stun its prey. The collapsing bubble also generates a burst of sonoluminescence, a flash of light so intense that it can be seen with the naked eye. The intense heat and pressure generated within the collapsing bubble are thought to be lethal to small organisms, adding an extra layer of effectiveness to the shrimp's attack. The pistol shrimp's remarkable ability to generate light from sound is a testament to the power of evolution to shape even the most unexpected adaptations.
Section 5. Unraveling the mystery, the ongoing debate and future of sonoluminescence. Despite decades of research, the exact mechanisms behind sonoluminescence are still a subject of debate among scientists. While the basic principles are understood, sound waves, collapsing bubbles, and generating extreme conditions, the details of how light is produced remain elusive. Several theories attempt to explain the phenomenon, each with its own strengths and weaknesses. One prominent theory suggests that the intense heat within the collapsing bubble strips electrons from their atoms, creating a plasma. Another theory proposes that shockwaves generated during bubble collapse are responsible for heating the gas inside. leading to light emission. The quest to understand sonoluminescence is not merely an academic exercise. Unlocking its secrets could pave the way for exciting new technologies. The future of sonoluminescence research is bright, filled with the promise of groundbreaking discoveries and innovative applications.